Okay, what are the rules that we're going to follow? Well, here, let's start with looking at a typical basic sorting problem. Say a university has student records. And for every student, there's a certain amount of information. Maybe there's a class number, there's a grade, there's a phone number, maybe an address. So we refer to an item as a record, or the information that we're going to sort. But in particular, there's a piece of a record called a key. And what we want to do is put the records into order according to the key. That's the sort problem. Rearrange an array of n items into ascending order according to a defined key, which is part of the item. Now, our goal is to be able to sort any type of data. So let's look at a couple of client programs. First example is to just sort some random real numbers into ascending order. So here's a client that calls our insertion sort method. And all it does is read numbers from standard input, then into an array A, then calls insertion sort, and then prints them out. And you can see on the right that the numbers are printed out in sorted order. This seems like an artificial kind of input, but actually we'll look at an application even in this lecture. And there are many applications where random inputs are a fine model. Here's maybe a more familiar sort client that sorts strings. And in this case, it reads the strings from a file using our read strings method in our in class, which takes a file as argument. So we take the file name as the first command line argument, read in an array of strings from that file separated by blanks, call our insertion sort method again. So insertion.sort is a method that takes an array A as its parameter and it as its first argument, and it rearranges the strings in that array to be in sorted order. So in this case, words3.text has a certain number of three-letter words, and this client program will result in those three-letter words being rearranged into alphabetical order. Here's another client that we could use our sort program for if we achieve the goal of sorting any type of data. In this one, we're going to sort the file names in a given directory. So again, we use the file class from Java, and we go and use the list files method from that class to get an array that contains all the file names in the given directory. And that's an array with file names in it, and insertion sort takes that array as its first argument, and again sorts them, and then we go ahead and go through them one by one and print them out, and they come out in order of file name. So that's three different clients, three completely different types of data. And the first rule of the game that we have to think about is, how can we make it so that we can implement one sort program that can be used by these three different clients to implement three different types of data? And the way that that happens is a mechanism known as a callback. So that's our basic question. How can sort know how to compare data of all these different types without being given any information about the type of an item's key? And the answer is that we set up a mechanism known as a callback, or a reference to executable code, where the client, by passing an array of objects to the sort function, in Java, there's an implicit mechanism that says that any such array of objects is going to have a compare to method. Then the sort function calls back the compare to method associated with the objects in the array whenever it needs to compare two items. There's a lot of different ways to implement callbacks, and that's programming language specific. Different languages have different mechanisms. It's all about the idea of passing functions as arguments to other functions, which is a deep area that gets us into functional programming and thinking all the way back to Turing and Church. For Java, because of the desire to check types at compile time, they use a specific method called an interface. And we'll look at the details of how to implement callbacks with Java interfaces now. It's a little bit of programming language detail, but it's really worthwhile because it allows us to use the sorts that we develop for any type of data in a type-safe manner. So we already looked at some clients. This is the example of the client program that sorts the files in a given directory by file name. So it just calls our sort method with an array of some type of object as first argument. Now, built into Java is the so-called comparable interface. And all the comparable interface is a specification that a data type that implements comparable will have a compare to method. And it's generic, it'll be compared to against a certain type of item. Now, when we implement objects that are to be sorted, we'll implement the comparable method. That's up in the top. Class file implements comparable file. And since sorting is an operation that's used in so many situations, many of the standard Java types that you would expect to involve sorts will implement comparable. And all that means is that that data type has an instance method that will implement the compare to method. It'll compare this object against the object given as argument, and depending on some complicated test, it'll return -1 meaning less, +1 meaning greater, or 0 meaning equal. Now that compare to method is really all that the sort implementation needs. First, it says that it's going to take as argument an array of type comparable. So that means the objects in the array are going to implement the comparable interface, or that they'll have a compare to method. And then the sort code can just use that compare to method invoked on an instance of the object like an entry in the array, and as argument another instance in the object like another entry in the array, to test whether the first is less than the second, as in this example. The key point is that the sort implementation has no dependence on the type of data. That's handled by the comparable interface. And a different comparable array will be sorted in the same way. They'll eventually, because of the interface mechanism, be a call back to the actual compare to code that goes with the type of object being sorted. Now, there's a few rules in there, natural rules, but they're worth talking about and paying attention to, that the compare to method has to implement. And it's so-called a total order. And all that's saying is really that it must be possible to put items in order in a sort. So there's three properties. First one says that if v is less than or equal to w and w is less than or equal to v, then the only way for that to be true is if they're equal. And then there's transitivity. If v is less than w, w is less than x, then v must be less than or equal to x. And totality is that either v is less than or equal to w, or w is less than or equal to v, or both, they're equal. And there's plenty of natural total orders in the types of data that we normally want to consider for sort keys, like integers or natural numbers or real numbers, or alphabetical order for strings, chronological order for dates or times, and so forth. The cartoon on the right shows that not all orders are necessarily total orders. So rock, paper, scissors is intransitive. If you know that v is less than w, w is less than v, you don't know that v is less than or equal to v. I'm sorry, v is less than w, w is less than or equal to x, then you don't necessarily know that v is less than or equal to x. All right, so the comparable API, then by convention in Java, we always need to implement compare to such that v.compare to w is a total order. And also by convention, it returns a negative integer if it's less, 0 if it's equal, positive if it's greater. If this object's greater than the object given as argument. If the types are incompatible, or if either one is null, compare to should throw an exception. Now, again, many of Java's standard types for numbers and dates and file and so forth implement compare to by convention. Now, if we're going to implement our own type, then we have to go ahead and implement the comparable interface according to these rules. And usually that's fairly straightforward. So here's an example. It's a simplified version of the date class that's implemented within Java, just to show the idea of implementing comparable. So after the class declaration, we write implements comparable, and then we fill in the generic with the same type because we're only going to compare dates to other dates. In this implementation, the date class has 3 instance variables: the month, the day, and the year. And the constructor fills those in from the arguments, as you can see. So now if you want to compare 2 different dates, then the first thing to do is to check if this year is less than that year, and where that is the year given, the date given in the argument. If that's true, then it's less, return -1. And if the year is greater, return +1. Otherwise, the years must be equal, so we have to look at the months to do the compare, and so forth down to do the days. Only if they're all equal do we return 0. So that's an example of an implementation of comparable by implementing the compare to method to put dates in order, as you might expect. So the Java language helps us with this comparable mechanism so that we can sort data of any type. But when we come to implement sorting algorithms, we're actually even going to hide that beneath our own implementations so that our sorting algorithms actually, the actual code, can be used to implement sorting in many other languages. And the way we do that is to take the 2 primary operations, compares and exchanges, that we use to refer to data and encapsulate them just as static methods. So we're going to use a method less that takes 2 comparable objects as arguments, and it just returns v.compare to w less than 0. And then the other thing that we do when we sort items that are in an array is to swap or exchange the item at a given index I with the one at a given index j. And that's every programmer's first introduction to assignment statements. We save A of I in a variable swap, put A of j in A of I, and then put swap back in A of j. So now our sort methods to refer to data will just use these 2 static methods. And there's a good reason for that. Here's an example. Suppose we want to test if an array is sorted. So this is a static method that is supposed to return true if the array is sorted and false if it's not. And all it does is just go through the array from 1 to the length of the array and test if each item is less than the one before it. If you have an item that's less than the one before it, then it's not sorted, you return false. If you get all the way through the array without that happening, then you say the array is true. That's pretty simple code. The question is, if you have a sorting algorithm that passes that test, are you sure that it correctly sorted the array? Well, the answer to that question is yes, if you used only the less than exchange methods to implement, to refer to data. Because then you know, because you use the exchange method, that the data in the array after the sort is the same data as was in the array before the sort. If you have a sort method that can store any values in an array, it could, for example, store zeros in every array entry. That method would pass this test, but it didn't really correctly sort the array because it overwrote all the values. So we use less than exchange to be sure that we can test that our methods work with a method like this. The first elementary sorting method that we're going to take a look at is an easy method known as selection sort. The idea of selection sort is to start out with an unsorted array, and we'll use these playing cards as an example. In the ith iteration, we go through the array to try to find the smallest remaining entry. In this case, the 2 is the smallest remaining entry. And then we'll swap that with the first entry in the array, and then we know we've got one step done. Selection sort is based on iterating that idea. Okay, so the basic selection sort method is to, in the ith iteration, find the smallest remaining entry to the right of I, or bigger index than I, and then swap that with I. So when we start out, I's at the left end, and then all the remaining entries are to the right. We scan through, and the smallest one is the 2, 3 entries from the right. So we swap that. So that's the first step. Now that part of the array to the left of I is in its final order, and we simply continue. So now the smallest is the 3, swap that with I, increment I. So now we have the 2 and 3 in order, and continue in that way. Find the smallest, it's the 4, swap that one with I, increment I. Find the smallest, it's 5, swap that with I, increment I. Find the smallest, swap that with I, increment I. Each time we have to scan through all the remaining entries in order to find the smallest, but then once we found it, we only have to swap 2 cards. Those are both key properties of selection sort. Now the 8's the smallest, and we swap. And now we know they're in order, but the program doesn't, so it has to look and decide that I and min are the same, and then it swaps it with itself and does the same thing for the last. And so after that process, then we know that the entire array is in its final order, all sorted. All right, so one way to understand the way that an algorithm works is to think about invariance. So for selection sort, we have a pointer, that was our variable I, that scans from left to right. That's indicated by a little red arrow in this representation. The invariants are that the entries on and to the left of the arrow are never change, and they're in ascending order. No entry to the right of the arrow is smaller than any entry to the left of it. That's the way that we set it up. And the algorithm maintains those invariants by finding the smallest entry to the right and exchanging it with the next one. So the code implements the invariants. So to move the pointer to the right, we increment I. So now the invariant might be violated, so we have to fix it. It might be violated because you might have an element to the right of the pointer that is smaller than the element on the pointer. So what we have to do is identify the index of that minimum entry and exchange it. Then once we've exchanged it, again, we've preserved our invariant. After that point, no element to the left of the pointer is going to change, and there's no smaller element to the right. And that gives us immediately our code for the selection sort implementation. We identify the length of the array, that's in n. Then we have a for loop that goes through every element in the array. We keep a variable min, that is the index of going to be the index of the smallest element to the right of pointer I. We have an inner for loop that for j, if it finds a smaller one, resets min. And then once we've looked at all the elements to the right of I, we exchange the smallest one with I. That's a complete implementation of selection sort. Now, it's easy to develop a mathematical model for the cost of selection sort, and here's the proposition that describes that. Selection sort uses about n squared over 2 compares and exactly n exchanges. And just looking at this trace of selection sort in operation really is visual proof of this proposition. In this diagram, the entries in black are the ones that are examined in order to find the minimum each time, with the minimum in red. Entries in gray are not touched. They're in their final position. Well, you can see that this is going to be, in general, an n by n square, and about half of the elements in the square are black, or about n squared over 2. And you can see also the exact formula, n minus 1 plus n minus 2 and so forth, is the total number of compares used. And then on each of the n values of the variable I, there's an exchange. So that's the cost in terms of the number of exchanges. Now, what's interesting about this proposition about selection sort is that it doesn't matter what order the input is, selection sort's going to use quadratic time, because it always has to go through the whole thing to look for the minimum. Another property is that you can't sort moving less data, because selection sort does just a linear number of exchanges. Every item is put into its final position with just one exchange. Let's look at an animation of selection sort in operation. You can see our pointer moving from right to left. And every time it finds the smallest element to the right, it exchanges it into position. Now, if the array is partially sorted, doesn't matter to selection sort. Still has to go through, even if it's totally sorted, still has to go through to decide where that minimum element is. That's selection sort, our first elementary sorting method. Now we'll look at insertion sort, which is another elementary method that, interestingly, has quite different performance characteristics than selection sort. Let's look at a demo of insertion sort. For insertion sort, what we're going to do is we'll move an index I from left to right as before, but now in the ith iteration, we're going to move AI into position among the elements to its left. Let's look at how that works on our example with cards. So now we start by initializing I at the first card. And we take the idea that everything from I to its left is going to be sorted, and everything from the right we're not going to look at all. So everything to the left of I is in ascending order. Everything to the right we haven't seen at all yet. So now when we increment I, well, in this case it's already in order. We don't have anything else to do. In the third case now, when I is at the third entry in the array, now we start a index j, and we move that starting at I to the left, and what we need to do is just exchange the 5 with every element to its left that's greater. So first we exchange it with the 10. It's still not in place, so we exchange it with the 7. Now we get to the beginning of the array, and once we've done that, or we've hit a smaller element, then we have everybody to the left of I in order. So now we increment I again, and we come to the 3. Again, we exchange as long as the card immediately to the left is greater. And once we've done that, then we have everything to the left of I in ascending order. Now, in this case, we have the 8. We only have to exchange 1, and now it's got the 7 to its left, and everything is in order. So we've achieved putting it in order with less work in this case. We don't always have to go all the way back to the beginning. 4, exchange it with everybody to its left that's greater until we find a smaller element, and then it's in ascending order. 2 has to go all the way back to the beginning. But then the very next one, the 9, has to only go back 1 position. And the 6 has to go about halfway back. And then we have the entire array sorted. Again, we can look at insertion sort in terms of invariance. Our pointer still scans from left to right, but now the elements of the left of the pointer, including it, are in order, but the elements to the right have not yet been seen at all. So we have to look at the code that's going to maintain that invariant as the pointer increments. Move the pointer to the right, it's incremented again. Now the invariant's broken because the element on the pointer is not in sorted order. To put it in sorted order, we have to move from right to left, exchanging it with every larger elements to its left. And that's what the code at the bottom does. It starts J at I and decrements J, exchanging J with the elements to its left, A of J with the element to its left, A of J minus 1, as long as A of J is less than A of J minus 1, or J is bigger than 0. And that immediately gives this code for insertion sort, which is similar to our code for selection sort and just as simple. It's got 2 nested for loops. Selection sort had 2 nested for loops, a test, a comparison, and an exchange inside the for loop. And that's a fine implementation of an elementary sorting method. What about the analysis of insertion sort? It's more complicated. Our proposition says that insertion sort, to sort randomly ordered array with distinct keys, it'll use about 1/4 n squared compares and about the same number, 1/4 n squared exchanges on the average. This is more complicated to prove. It depends on the array being randomly ordered. And again, you can get a feeling for where the proposition comes from by looking at this n by n trace. Again, the black elements are the ones that we compare, and actually they're also the exchanges. And the red one is the one that's finally put into place. And you can see that for a large array that's randomly ordered, the element that we put into place is going to go about halfway back on the average. So that means about half of the elements below the diagonal are going to be black on the average. There's n squared over 2 below the diagonal. Half of that is n squared over 4. The analysis, exact analysis, is not much more detailed than that. This is a bigger trace that shows, again, about half the elements below the diagonal are involved in the sort. Let's look at an animation. Since n squared over 4 versus n squared over 2, insertion sorts are going to be about twice as fast as selection sort. So we can do about twice as many items in the trace in the same amount of time. It grabs an element, brings it back into position every time. So that's an animation for randomly ordered items. Now, insertion sort does depend on the initial order of the data. Let's look at the best case and the worst case, which are certainly outliers. If the array happens to be already sorted, all insertion sort does is really validate that. Each element has got a smaller elements to its left, so it does no exchanges. It gets the sorting job done with just n minus 1 compares. On the other hand, if the array is in descending order and it's no duplicates, then every element goes all the way back. It makes n squared over 2 compares and n squared over 2 exchanges. So in the first case, it's much, much faster than selection sort, linear instead of quadratic. In the second case, it's slower than selection sort because it uses about the same number of compares, but it uses many more exchanges. So let's see that in the animation. So this is when the items come in reverse order. Now, every time it gets a new item, it has to exchange it all the way back to the beginning. Same kind of dynamic characteristic as selection sort, except for every step, it's not just comparing, it's also exchanging, which makes it even slower in practice. So this is a bad case that we wouldn't like to see in a practical application. But there's also a good case that actually we take advantage of in plenty of practical applications. And that has to do with when the array is partially sorted. To talk about this in a quantitative way, we define what's called an inversion. An inversion is just a pair of keys that are out of order in the array. So this array has 6 inversions. T and R are out of order because R should go before T. T and P are out of order, and so forth. This array has 6 inversions. And we define an array to be partially sorted if its number of inversions is linear, if it's less than some constant times n. And partially sorted arrays appear often in practice. For example, if you have a large array with just a few that's sorted except for just a few unsorted elements appended at the end, it's going to be partially sorted. Or another case is if you only have a few entries out of place, the array is going to be partially sorted. These types of things arise often in practical applications. And what's interesting about insertion sort is that it runs in linear time for partially sorted arrays. And the proof is the number of comparisons and the number of exchanges is equal to the number of inversions. Number of exchanges equal to the number of inversions, and then there's an extra compare for every element except the first. So let's look at how that looks in the animation. Here's a partially sorted array, and you can see that insertion sort quickly gets the job done. We're going to take advantage of this a little bit later in this lecture. That's insertion sort, our second elementary sorting method. Now we'll look at shell sort, which is a bit elementary on the face of it, but it's not at all elementary, as you'll see. The idea of shell sort is that insertion sort is inefficient because elements really move only one position at a time, even when we kind of know that they have a long way to go. So the idea behind shell sort is that we'll move entries several positions at a time. And the way we're going to do it is called H-sorting the array. So an H-sorted array is H different interleaved sorted subsequences. So in this case, with H equals 4, if we start at L and look at every fourth element, M, P, T, then it's sorted. If we start in the second place at E and look at every fourth element, it's sorted. So this is 4 interleaved sequences. That's a 4-sorted array. And what we're going to do is implement a sorting method that H sorts for decreasing sequences of values of H. This is one of the oldest sorting methods invented by Shell in 1959. So in this case, it starts out with the input example shown, and then a 13 sort, a few items are moved, a 4 sort, a few more are moved, and then finally a 1 sort. And the idea is that each of these sorts can be implemented with only a few exchanges, given that the previous ones happened. So first thing is, how do we get an array H sorted? That's actually pretty easy. We just use insertion sort, but instead of going 1 back every time we come with a new item, we go H back. So for example, when we come to this A in the insertion sort, then we look at the array before that, and there was M and E in the positions 3 back. So we exchange the A with the larger one to its left, that's M, and then the other larger one to its left, that's E, and then put it into position. So the code is the same as for insertion sort, except that when we go backwards through the array, we skip by H instead of just by 1. That's how we H sort an array. And the idea is we're going to use insertion sort for 2 reasons based on our understanding of how insertion sort works. Well, the first thing is if the increments are big, then the size of the subarrays that we're sorting are pretty small, so any sorting method, including insertion sort, is going to work well. But the other thing is, if the increments are small, because we've done previous H sorts for bigger values of H, the array is partially sorted. And so insertion sort is going to be fast. It wouldn't work to use shell sort as the basis for H sorting, because that always takes quadratic time no matter what order there is in the array. So let's look at an example of shell sort with increments 7, 3, and 1. So we start with the sort example, and then 7 sorting it just involves doing insertion sort, but just reaching back 7 each time. In this case, the 4 subfiles stretched out at 7 each only have 2 elements in them. and then we 3 sort. Now, because it's 7 sorted, in the 3 sort, elements are either already in place or only go back a few strides. In this case, it's only the A that goes back 2. And then we 1 sort. And again, because of the fact that it's been 7 sorted and 3 sorted, the array is almost in order when it comes time to do the 1 sort, and most of the items only go back 1 or 2 positions. So we have to do a few extra passes to do the higher sorts, but each element moves only a little bit on each pass, and that's how shell sort gains its efficiency. Actually, once you 1 sort, that's insertion sort, so you're going to always get a sorted result. The only difference is how efficient is that. Now, the intuition behind shell sort, and actually the mathematical fact, is that if you've got an array that's H sorted and then you K sort it for another value, K different from H, it's still H sorted. This is one of those mathematical facts that seems obvious, but then if you try to prove it, maybe it's a little more subtle than you think. So if you think of all this as trivial and easy, go ahead and try to write down a proof that a G-sorted array remains G-sorted even after it's H-sorted. But most people will accept that, and it's a fact, and that's how shell sort gains its efficiency. Now there's another problem, is what increment sequence should we use for shell sort? One of the first things you might think of is, let's try powers of 2. Actually, that one doesn't work at all, very well at all, because it winds up not comparing elements in even positions with elements in odd positions until the 1 sort, which means performance can be bad. Shell's original idea was to try powers of 2 minus 1, and that works okay. Knuth, when he wrote his books in the 60s, proposed the increment sequence 3x plus 1. You start with a 1, 4, 13, 40, 121, 364, like that. And that's good because it's easy to compute. When we're using in shell sort, of course, we find the largest increment less than our file size and then do the sorts for decreasing values of that increment. But finding the best increment sequence is a research problem that has confounded people for quite a long time. Here's an increment sequence that I found after maybe a year's work, and it works well, but nobody knows if that's the best one. So here's the implementation in Java of shell sort for Knuth's 3x plus 1 increment sequence. We just go ahead and compute the increments that are less than n over 3, and then starting at that increment, whatever it is, and say we start at 364, then next time we need an increment, we just divide by 3. 364 integer divide by 3, 364 integer divide by 3 gives 121, 40, and so forth. So this h equals h over 3 gets us to the next increment. And then the implementation is just insertion sort. We just go through starting at h for I, and when we do the insertion, the j loop, we decrement j by h each time. Otherwise, the code is exactly like insertion sort. So just adding this extra loop for h sorting and this extra loop to compute the increments to insertion sort, we get a slightly more complicated piece of code, but it's much, much more efficient. Here's what it looks like for a bigger array. We start with randomly ordered input. And you can see that it gets more and more in order on each time that we h sort for the decreasing values of h. Here's an animation. This animation does the whole h sort for each subarray. It gives a little better feeling for what's going on. And now it did the high ones pretty quickly, and now it's doing the 1 sort. And again, it zips through the array pretty quickly. If it's partially sorted, it doesn't make much difference. Does the higher order sorts a little bit faster. But that's a simple to implement and very efficient sorting algorithm. Now the analysis of shell sort is still open. There's a few things that we can say. For example, we can say that the number of compares in the worst case is big O of n to the 3/2 for the 3x plus 1 increments. But actually, in practice, it's much less than that. Problem is, nobody knows an accurate model for describing the number of compares taken by shell sort for any interesting increment sequence. They seem to be with a small value multiple of n times the number of increments used, which is some multiple maybe of n log n. But nobody's been able to find an accurate model that proves that for any interesting increment sequence for shell sort. So why are we interested in this algorithm? Well, it's a simple idea that leads to substantial performance gains. It's very useful in practice because it's pretty fast, except for very huge arrays. It's going to beat even the classical sophisticated methods for medium-sized arrays. And it doesn't take much code. It's often used in embedded systems or in hardware sort type systems because there's so little code involved to implement it. And it just leads to a lot of interesting questions. This gets to the intellectual challenge of developing algorithms. If you think what we've been studying so far is trivial, go ahead and find a better increment sequence. Try some technique to discover one. And try to say something about the average case performance of shell sort. People have been trying to do that for 50 years without a whole lot of success. So the lesson is that we can develop good algorithms or good implementations without much code, but there's some out there that are still waiting discovery. It could be that there's some increment sequence out there that makes shell sort more efficient than any other method, any other sorting method that we know for practical file size. No one can deny that. That's shell sort, our first non-trivial sorting method. Next, we're going to look at an easy application of sorting to a related problem called shuffling. So suppose you have a deck of cards. One of the things that you might want to try to do is to simply rearrange those cards into random order. That's called shuffling. Here's a way to get shuffling done using a sort. It seems like the opposite. The idea is just generate a random real number for every array entry and then sort using those random numbers as the keys. That's an effective way to get things shuffled. And it's possible to prove that that produces a uniformly random permutation of the input if there's no duplicate values, assuming that you have real numbers that are generated uniformly at random. And that just means that it's well shuffled, that every possible way of shuffling the deck appears with equal probability. That's fine, but it requires a sort, and the sort seems like a lot of work for this problem. And the question is, can we do better? Can we have a faster way to shuffle? Do we really need to pay the cost of a full sort? And the answer to that question is no. There's actually a very easy way to rearrange an array so that the result is a uniformly random permutation and only require linear time to get the job done. Let's look at a demo. The idea is to pass through the array from left to right with an index I, as we've been doing. But now we start with the array in order, and actually it doesn't matter how we start the array. And every time we pick an integer between 0 and I uniformly at random and swap A of I with that integer. So let's look. At the beginning, we don't do anything. We just swap it with itself. Now with I equals 2, or I pointing to the second card, we generate a random integer in this, between 0 and I. In this case, it's the one to the left, and we swap those. Increment I, generate a random integer. This time it's going to be the first one again. Swap them. Increment I, generate a random integer. Swap them. Increment I, generate a random integer. Swap them. And continue in that way. Swap. So for every I, we do exactly one swap. Now, a card could be involved in more than one swap, but that's not an issue. The point is that the cards to the left of I are shuffled. They're uniform randomly shuffled. In this case, I and R are the same. There's no swap. Increment I, generate a random R, swap them. And at the end, we have the deck shuffled. That's a linear time shuffling algorithm making use of randomness. It was proved actually a long time ago, even before computer implementations, that if you do that, you get a uniformly random permutation, and it only takes linear time. So that's definitely a way to get a deck shuffled quite easily. Easy to implement. Now it's key that the uniform random number be between 0 and I minus 1. You'll often see programmers thinking that they're implementing a shuffle and they just choose for every entry, they just choose a random place in the array to exchange it with. And that doesn't really work. You could do the items between I and the n minus 1, the ones that you haven't seen yet, and that would also work. But doing the whole array doesn't give you a uniformly random result. With that one caveat, this code is almost trivial. And it's a method in our standard random class. Now, if you're going to be using random methods that depend on randomness in real applications, you do have to be careful. So this is just an example about software security. There's a lot of difficult and deep issues to worry about in software security, and we're not going to worry about all of them. But one thing that we can do is make sure that our algorithms work as advertised. So here's an example of an implementation for online poker. Here's the code that you can find on the web for how to shuffle a deck of cards. That's pretty similar to our code, but it's actually got a few bugs, more than a few bugs. So first one is the way that random works, it actually never gets to 52. Which means that the last card just stays, it can't end up in the last place. So it's definitely not shuffled because of that. Maybe that one's minor, but it also is picking a random card from the whole deck. And as we just pointed out, that's not uniform. Should be between 1 and I, or between I plus 1 and 52. Another problem is in this implementation that the random uses just a 32-bit seed. That if you do that, there's not enough possible shuffles. The number of possible shuffles is much more. If n is 52, it's 52 factorial, which is a lot bigger than 2 to the 32nd. So it's not close to random or uniform. And the other thing is that the seed is just the number of milliseconds since midnight, and that cuts down the number of shuffles even more. And in fact, didn't take that much hacking for someone to realize that after seeing 5 cards and figuring out what the server clock was doing, you could get all the future cards in real time in a program. And that's a pretty tough thing to have happen if you're implementing online poker. You might want to make sure that if you're advertising that you're doing a random shuffle, that you go ahead and do so. A famous quote, and there's many similar quotes, the generation of random numbers is too important to be left to chance. So if your business does depend on shuffling, people have looked at all sorts of options, including using hardware random number generators, and there's various tests available to make sure that it's random. And you better use good shuffling code. That's our topic. But the bottom line is, don't think that it's easy to shuffle a deck of cards. So that's shuffling, our first non-trivial sorting application. Now we'll look at an application of sorting from the field of computational geometry for an interesting computation. If you have a set of endpoints in the plane, there's a geometric object called the convex hull, which is the smallest polygon that encloses all the points. There's the convex hull for that set of points. There's a lot of equivalent definitions of this, some of them very mathematical that extend to higher dimensions. It's the smallest convex set that contain all the points, the smallest area convex polygon enclosing the points. It's a convex polygon that encloses the points whose vertices are points in the set. Those are all equivalent definitions. And what we want to do is, given a set of points, we want to have a program that can give us the convex hull. Now, what should the output of such a program, such a method be? Well, in order to be able to work with the result, it should be a sequence of vertices that gives us that polygon if we follow it. If we've got some points that are on the boundary but aren't really vertices, they shouldn't be included. This points out examples of how difficult computational geometry can sometimes be, because degenerate cases like this are difficult to deal with in code. We're not going to spend a lot of time on this in this lecture, but it's something always to be aware of when trying to apply simple algorithms in situations like this that turn out to be maybe more sophisticated than we might think. Oh yeah, gotcha. Mm-hmm. Well, there's actually a way to compute the convex hull just mechanically. If you put nails around the points and put a rubber band around it, that gives you the convex hull. Now, we're not going to be able to really implement that in a computer program, but it's surprising how well we can do. Here's an application where people want to compute the convex hull. Suppose you have a robot that wants to get from S to T, and there's an obstacle that's defined by some polygon. You want to be able to go around the obstacle, and it turns out that the shortest path, either it's a straight line from S to T, or it's part of the convex hull. And it's not hard to see why that might be true. There's plenty of other applications where people want to be able to compute the convex hull. Here's another application. If you want to find the pair of points that are the farthest apart in a set of points in the plane, this is sometimes important in statistical calculation or other applications. They're on the convex hull. If you have the convex hull, this computation is easy. They're going to be extreme points on the convex hull. So there's a lot of geometric properties of the convex hull that we can take advantage of to develop an algorithm. And here are two properties. Now these are things that have to be proven, and we're not going to get into the details of geometric proof, but they're intuitive, and you'll certainly have no trouble accepting that these things are true. One thing is that you can traverse the convex hull by making only counterclockwise turns, or left turns if you're looking at the screen here. And the other thing is that, so if we travel from P to point 1, then we make a left turn to go to point 5, or a counterclockwise turn, and then from there we go to point 9 and 12, and then we eventually get back to the start point. The other thing is, if you take the point with the lowest y coordinate, and then if you look at the polar angle with respect, for every other point with respect to that one, so the angle you get from the x-axis through P up to the point, then the vertices appear in increasing order of that angle. And again, that's not difficult to see that that's a fact. And the algorithm we're going to look at, called the Graham scan, is based on those two facts. It's the idea is to start with point P, the one with the smallest y coordinate, sort the points by polar angle with P, that is, we're just going to consider them in that order, And then we'll just throw away the ones that do not create a counterclockwise turn. And you'll see how that works when we look at a demo. So we start at point P, sort the points by polar angle with P. So that is, if we take a vertical line and sweep it in a counterclockwise direction, what order do we hit the points? The first thing we hit is 0, 1, and then if we sweep counterclockwise, we get to 2, and then 3 and 4, and so forth. So that's the ordering of those points. And so now we'll just consider those points in order and then take them for the convex hull. At the beginning, 0, 1 is a line that's on the convex hull. So the point with the lowest y coordinates on the convex hull, and so is the one that is the smallest polar angle it creates with the x-axis. So now what about this one, 2? Is that on the convex hull? Well, as far as we know at this point, it could be. It could be that the thing is a triangle and 0 is the last point, in which case it would be. But it's and same with 3. As far as we know, that one could be on the convex hull. But as soon as we go out to 4, that's not a counterclockwise turn. It's going the wrong way. And essentially what this means is that point 4 is evidence that there's no way that point 3 can be on the convex hull. You can convince yourself of that quite easily. So we just throw point 3 out. It's not on the convex hull. So, and what about the angle from 1 to 2 to 4? That's not counterclockwise either. That's turning the wrong way. That's turning to the right. So point 2 can't be on the convex hull either. And indeed, if you just draw the line from 1 to 4, you can see the 2's inside. So there's no way it could be in the convex hull. That's essentially the proof that you have to have a counterclockwise turn. So now we go on to 5. Turning the wrong way, so point 4 can't be on the convex hull. So now we go to 6. As far as we know, it could be, but as soon as we hit 7, we know that it can't be because that's a right turn. So 6 is not there. Go to 8. Nope, 7 can't be on the convex hull. Go to 9. 8 can't be on the convex hull. Now we go to 10 and 11. As far as we know, they could be. If 12 weren't there, they would be. But as soon as we hit 12, we see that 11 can't be on the convex hull and 10 can't be on the convex hull. And that completes the computation of the convex hull with the Graham scan. Okay, so there are a number of implementation challenges for the Graham scan, and we're not going to go into detail on these because this is a lecture on sorting algorithms, not computational geometry. But it is indicative of how, even if we have a good sort, we might have to do some extra work to actually solve our problem in an application. So how do we find the point with the smallest y coordinate? You could sort. You could define an order and compare the points by y coordinate. Essentially sorting is the answer to that question. And we'll look at the next lecture of what it means to define ordering among objects, a little more general than what we do for sorting. How to sort the points by polar angle. Well, again, we need to define what we mean when we're comparing points. And in the next lecture, again, we'll look at ways to define different orderings among points. And Graham scan's a perfect example. We don't want to just be able to sort things. We don't want to just be able to sort them by defining a compare to. We want to be able to sort the same things in different ways sometimes. And this example is a fine motivation of that. Figuring out whether what we have is a counterclockwise turn, that's a little exercise in geometry, and we'll just talk about that briefly on the next couple of slides. And then, what about getting the sort done efficiently? Well, we could use shell sort, but actually in the next couple of lectures, we'll look at classical sorts, merge sort and quick sort that we could use. The idea, though, is that this example illustrates that a good sorting algorithm gives us a good complex call algorithm. That's an extremely important principle in designing good algorithms. Once we have a good algorithm, if we have another problem, we can say to ourselves, well, we've got a good solution to this algorithm. Can we use that solution to solve our new problem? Convex hull, when we have a good sorting algorithm, it gives us a good convex hull algorithm, because the most work in convex hull is the sort. And then again, there's all kinds of difficulties in implementing convex hull in real world situations because of various degeneracies. And these things are covered on the book site. So the main part of computation that we haven't really talked about, and we'll cover briefly, is if we have 3 points, A, B, and C, and you go from A to B to C, are you making a counterclockwise turn or not? So in the example at the left, A to B to C is counterclockwise. The example at the right, A to B to C is not counterclockwise. If you're going from A to B, you turn left to get to C in the first case, and you go right to get to C in the second case. And we want to do a computation that distinguishes this. Now, this computation would be pretty easy, except for the degeneracies, is what do you want to count it if they're all on the same line? Or if the slope is infinity. So you have to just be aware that these situations have to be dealt with. So the code isn't quite as simple as you might come up with in the first instance that you try. So there's degeneracies to deal with and floating point precision. But researchers in computational geometry have worked this out. And actually, there's not that much code at all in the end involved. And this is a slide that gives the math. And I won't talk through this math. If you're interested in implementing this, you can come back to this slide. And it's essentially based on the idea of computing the slopes of the lines between A and B and between A and C and comparing them to decide whether you're turning counterclockwise or clockwise. And this is the specific math that gets that implemented. This is if we implement a point data type for computational geometry, it can have a method, CCW, that just with this little math calculation, b.x minus a.x times c.y minus a.y minus b.y, this calculation here gives you immediately whether it's counterclockwise, clockwise, or collinear. Not much code at all. And that method is the basis for the Graham scan. The Graham scan uses a sort where we give 2 different ways to sort the points. And it uses a pushdown stack for the hull. It puts the points on the hull, and it goes ahead and for every point, considering them in the order of the polar sort, it'll compare whether the top 2 points on the hull and the new point implement a CCW turn or not. And if it's not a CCW turn, it pops it and continues going. Very little code to implement the convex hull, given that you have a sort. And that's our main point for this lecture. There's many natural applications of sorting, but also we'll be able to develop new algorithms that use sorts that gain efficiency because of the efficiency of sorting.